right, thank you. Okay, it started recording, right? Okay. Well, hello everyone. As you know, my name is Valentina, and I'm an undergraduate student of aerospace engineering at the Florida Institute of Technology here in the United States. And I was in charge of the engineering center. So I'll talk to you a little bit about what I ended up designing here. Let's see. So some of the things that I'm going to talk about, first of all, is the internal design of my module. How I designed it, the things I incorporated, as well as the machines and the technologies that are necessary for the operation of my module. I'll talk about some of the resources that could be generated in situ in a Martian environment, but also those resources that need to be transported from Earth because you can't create everything. I'll talk about the organizational structure of my module and what the positions and the routines that my crew members are going to have to follow in order to keep this station running, as well as the training program that they'll have to undergo before even be selected for this mission. I'll go into the resources that are going to be needed in a week's time, 5 days, as well as the guidelines that are going to be provided to the other facilities in our station in order to keep everything running and well. Uh, I'll discuss the protocols and the routines that each of my crew members are going to be doing. This includes protocols of safety, of occupancy, for food microproduction, and the protocols for 3D printing. Additionally, I'll talk about the technologies and the outputs that doing this research in space environments can help on Earth, as well as the guidelines that can be applied to daily life on Earth if we follow these protocols and these technologies. And then finally, the impacts to the sustainable development goals that we have as a global society. So first I'll talk about the internal design. Mind you, I'm an engineer. I'm not a graphical designer, but I did attempt to draw my structures. Now, this is the first draft that I conducted. Oh, I'm sorry. What did I do? This is the first draft that I conducted for my station. I have 3 levels, and I just noted the basic things that I wanted to have going on. So obviously a food station, a bathroom, dormitories, lockers for storage and research components. But it wasn't what I ended up settling on. This is what I ended up drawing. This is my more final draft. Sorry. I'll go more in depth into every single component, but from what I can tell you right now, I designed my vertical garden is in the core of my station, and it is preceded by a spiral staircase all the way to the bottom. Now this design has many benefits, and architecturally speaking, and also biologically speaking, which I'll get into in a second. I also have a garage attached to the first level, and this will be, let me have a little pointer. Hold on. Oh, there we go. That's perfect. This will be a pressurized airlux chamber that'll lead to the other facilities of our station. Now, so the third level, when I was designing this, I also had to keep in mind, how can we improve mental health within my crew members? So I ended up integrating an observatory dome. This will allow my crew members to observe the Martian sky. I also, on the third level, have my engineering bay, so everything research related. I have a microscope so that my researcher can look into the sampling of the plants that we're growing, evaluate plant growth, stability, all those things. I have 2 3D printers up here, as well as a refrigerator in order for my researcher to store the samples that he or she is designing. I have some storage space. And then on my second level, I have my dormitories. This is where my lockers are for the astronauts. I also have on the back of the core, might not be able to see it, but I've designed a library to go there because again, we also want my crew members to have something to do that's recreational and not just work all the time. On this side, this component that you can't see, I would design a retractable table and retractable chairs so that if they're going to read a book, they can go and sit and read a book there, or if they're going to play board games and stuff like that. At the first floor, I have our little kitchenette equipped with a rehydrator in order to rehydrate our freeze-dried food. As well with the sink, some storage over here. I have a bathroom that includes a sink, a shower, and a toilet. And these work in a water recycling system that I'm gonna explain a little further. As I mentioned before, these are the pressurized chambers that lead to the other spaces. And this also goes accordingly to the 8 diameters that is necessary for transport. And then I have the garage over here. The garage is mostly going to be the technician's space. So a place for rovers. If I could draw a car, this is where it would go. So say they want to go explore the Martian terrain. Um, I don't know if you've ever watched any of those sci-fi movies where they have a rover where they, drive and study the environment more hands-on, sort of like an extravehicular activity, if you may. Additionally, here I have some backup batteries, storage systems, another 3D printer, hooks. On this side, I would probably have, or not on this side, but on this pressurized chamber, I would have a place where they can keep their suits, their spacesuits. That way they can put them on and then go into the outside environment. This what I had in mind when designing this little compartment is a fan. So to ventilate the dust that, comes with the dust storms in the Martian environment. Now, I'm going to talk about some of the technologies that come with my facility. Now, obviously, we have to take into account the life support systems and the habitat systems that enable life to actually be carried out in Mars. And the most important one is the oxygen regeneration unit. So how this works is that it extracts the dioxide from water via electrolysis or directly from the Martian carbon dioxide. And in addition to this, I have a carbon dioxide scrubber, which is similar to a process that NASA uses, and it utilizes lithium hydroxide or molecular sieves to filter carbon dioxide from the air, producing dioxide. In addition, and I talked about this a little bit earlier, I'll have a water recovery and filtration system. So it'll recycle the gray water and urine into potable water, leaving behind only the feces as waste, which that will be carried out by my waste management system. I'll have a temperature and humidity control system as it'll keep internal climate livable. As humans, we like to maintain our homeostasis and we are very wary of changes in our surroundings. So this will allow humans to live as normal as you can in Mars. Another one of probably the most important ones is a pressurization system. This will maintain breathable atmospheric pressure in all modules. Again, as humans, we don't like changes in our atmospheric pressure, which is when you go on a plane and you go to a place with different altitude, you experience different atmospheric pressure and you feel kind of stuffy. Yeah, we don't want that to happen. And then finally, an airlock chamber is probably one of the most important life support systems that you can have in a space environment. This will mainly be used for extravehicular activity preparation and preventing contamination into your actual module. I have 2 of those in my modular home. Now, I briefly touched on this earlier, but my vertical garden core that I have going throughout my station has various benefits. Its central placement will maximize light exposure, airflow, and structural symmetry. And the staircase spiraling around it ensures efficient circulation while passing through each level. So, in addition to acting as a food production source, it'll also act as an oxygenation tower, improving air quality on all floors. It'll integrate a gray water recycling to feed the hydroponic root systems. And this is just a little, wouldn't say it's defined, but on the top tier, I would have leafy greens, microgreens, and medicinal herbs, as it'll be easier for my researcher to study the herbs that are on the top floor, and that's where the engineering bay is. On the middle tier, I would have fruiting plants like cherry tomatoes or peppers because they're low weight. And then on lower tier, I'd have fast-growing rock groups that can easily be taken into the food station. Now, one of the most important power systems that are integrated into my garden core is that it'll have an automation and lighting system. So I'll have LED stripes that mimic Martian day-night cycles, which is 24.6 hours a day. I'll also have sensors for humidity, nutrient levels, and oxygen output. Now, as my researcher, researches and understands the conditions in which plants can healthily grow in Mars, these automation systems will uh, adapt to that and only use the energy that's necessary. Now, another really important part about living in a space environment is your engineering and fabrication and how you're going to give maintenance to these aspects. So most importantly is obviously a 3D printer. You can't transport everything you need from Earth to Mars. So I'm using regolith-based filaments for tools and parts. Recent literature has approved or is researching the use of regolith-based plastics for 3D printing filament. It's part of what my own personal research encounters here at Florida Tech. I'm researching the usability of human waste to be produced into bioplastic, into more specifically polyhydroxyalkanoate, which is a type of 3D printing filament. But that's still ongoing, and I'm writing, my papers and all that. But it's fun stuff. In addition to that, though, I will have a battery diagnostic station. So it'll just be me monitoring energy cells and storage units. And now I think I'm going to talk about my energy systems. Yes. So Jess did a great job yesterday about explaining, how power can be effectively used in Mars. I definitely loved her power station encompassing of energy. But I will say I will use solar panel arrays for mine as I'm not going to be using, as much energy. I'm not transmitting as much energy. So solar panel arrays will be my primary source of energy with tilting and tracking mechanisms. I recently spoke with the deputy, he was a deputy researcher at the at the NASA Mars office for exploration or something like that. It was a weird title. And he was talking about recent researches or literature that NASA is putting out about solar panel arrays that are able to not extract dust, but they're built different than when most solar panels look like, and they're used to utilize that Martian dust that comes from the dust storms and in order to be more effective. So they use that regolith for effectiveness. I'm not quite sure how that works. I haven't read into it, but I do think it's really interesting and I would utilize that. In addition, I have a compact nuclear generator. This is just for night cycles or dust storm conditions when the solar panel arrays aren't functioning as well as they could. I'll have a battery bank of lithium-ion batteries to store surplus energy. I know Simi mentioned yesterday the usability of plutonium batteries. However, I'm going to say that I'm going to be using lithium-ion batteries as I love their versatility and their usability. Also, they're much lighter, so lightweight systems is what we want in space travel, as every pound, every gram of cargo is extremely expensive. And also, I'm not quite a fan of the radioactivity that plutonium batteries come with. Now, I'll also have a power inverter and a load balancer. This is important as it'll stabilize the power flow to all of the modules in our station. The research that I'll have my researcher doing is going to encompass a bunch of different things, but mainly a plant growth monitoring system. We want to know if the plants we're growing here are as effective as they are when they're growing on Earth. For this, I'll have spectral imaging cameras or multispectral sensors that will track the plant health, photosynthesis, and growth rates, see if it actually assimilates to anything that happens here on Earth. I'll have, and this data will help me optimize light, humidity, and nutrients. As I said with my automation system earlier, this will help me adapt and reduce my energy usage in our center. I'll have a microbial detection system, either using a PCR or a DNA or RNA sequencing technology. So I want to monitor microbial growth in the habitat, make sure that mold or biofilm outbreaks aren't growing in these confined spaces, because if they are, that would be a really big challenge. Our food source is now moldy or producing biofilm that's not edible anymore. So that's important. That's an important thing that my researcher is going to be doing, as well as researching closed loop ecosystem analytics. So I'm going to have sensors around my core garden measuring oxygen production, carbon dioxide uptake, and nutrient cycling in the vertical garden. This is key to understanding bioregenerative life support systems in a Martian environment. So, but in addition to that, my technician will have, 3D printing experimental lab. So that means studying the material strength, tensile strength, reusability, and efficiency of printed parts. We don't know if UV ray lights or radiation or dust, Martian dust, will affect the versatility and the usability of these 3D printed plastics. That's another important thing to research if we have a station there. In addition to that, or in the same way, dust resistance testing rig is important as it will research the seal integrity, the clogging, and the wear of machinery and suits. We want to ensure that the suits we're wearing or the machinery we're using isn't going to break down, or if it is, we want to know how long it'll be until it breaks down. In addition to that, it kind of touches into a little bit of the idea that Jess had with the power station is a ground penetrating radar. But with this, I'll be studying underground structures, water ice deposits, or lava tubes just to get a more general understanding of the Martian environment. Sorry. So probably one of the most important research studies that you can conduct in a space environment is the monitoring of our own bodies, because we want to ensure that we're not decimating human lives through doing this. So biometric monitoring wearables is one of the key aspects of space travel, and it's already done. So they're, integrated into small garments or wristbands, and they just track your vitals, like your heart rate, your oxygen stat, your sleep, your stress, making sure that your body is functioning as well as it should be functioning. But in addition to that, especially for more long-term missions, it's important to look at the psychological effects that it can have on your well-being. So having journals to study the effect of isolation and stress in confined environments is a perfect way to monitor this. And then lastly, a metabolic analyzer. We want to ensure that the food we're growing, is actually feeding us and giving us the nutrients we need. Also, we want to track exercise efficiency and food conversion. And this will be using to measure the caloric input, the oxygen consumption, and the carbon dioxide production that's going on in our center. Now, I want to touch a little bit more about my dome observatory, because not only is it really pretty to look at, but also it's important to have. So astronauts living in this station can use it as a stargazing and observation center. So Mars has a thinner atmosphere. So stargazing is much clearer than on Earth due to the reduced atmospheric distortion and no light pollution. But also, and this is probably one of the most crucial facts or factors about it, is that the weather and dust storm monitoring. So any of the astronauts can offer visibility to incoming dust storms, wind direction, and potential hot hazards. Say they have an extravehicular activity and they need to observe the weather before going out. This would be perfect for that. And then lastly, it provides that psychological relief and inspiration that we've been talking about that is so very important in space travel. Being able to see the Martian sky and stars above would provide emotional and psychological benefits during long missions to these astronauts. Now, some of the architectural features of it would be that it's a transparent polycarbonate or maybe an aluminum silicate dome canopy. Uh, it'll ensure that it can withstand the Martian dust storms. It is integrated with a telescope or an imaging sensor for research. So another research topic we can do. You can do a lot of research in Martian atmospheres. You can go crazy with it. But I'll also have an HUG panel with star maps, atmospheric readings, and rover cams, so the astronauts know what they're looking for or looking at. And now here, so I'd completely forgotten we live in a day and age where you can feed almost anything to AI and it'll give you a rendition of what it thinks it looks like. So I fed it my drawing, the design I had done, the entire thing, and this is what it gave me, which looks straight out of a sci-fi movie, if you ask me. It's not exactly as I had imagined it, but it does a pretty well job at picturing what I want it to do. Because I feel like you can't really look at my spiral staircase. Trust me, it's harder than it looks like to draw something in a spiral. But this is the overall idea of what I had. Now, I want to talk about some of the resources that can be either produced in situ or transported from Earth. So my in situ resources that I can produce there is food. Obviously, with my vertical farming and my hydroponics or in aeroponics, I can provide nutrition and oxygen production to my station. Electricity is a big one. Using solar panels, energy storage systems, I can provide power for systems and research, keep my station running. Compost is, another really important one. So we need to have a proper waste management system, and composting provides a lot of that. So from food to human waste, you can create fertilizer for crops and stuff like that. Methane is a really important one that most times you don't really think about. So using a Sabatier reaction, it combines carbon dioxide and dihydride. Yes, to create fuel for return trips on rovers. But I do have to say another idea for this methane production is another of my research topics, and it encompasses fuel production in space using uh, chlorella which is a type of green microalgae. Now, if we can prove we can actually do that in space, it'd be, crazy because it'll pioneer experimentation into the production of fuels in space. So that's another idea. I could probably throw it in there. Uh, a great one is 3D printed tools. We can generate that there of using regolith derived filament or recycled plastics. This will help us for maintenance tools or small repairs to rovers, uh, stuff like that. And then nitrogen is also a really important one that most times you don't really think about. It's you can generate it from the small amounts in the Martian atmosphere, and it will be good for pressurizing our habitats, plant growth, all that stuff. Now, from Earth, I would very much transport seeds as they can't be synthesized, but they can be propagated. So that's a plus one that you get from living in an environment over time. Medicines and pharmaceuticals, although you could technically produce them, they're very sensitive to different conditions and they're complex to synthesize. So you might have a really hard time actually creating the pharmaceuticals, but it's nice knowing you could if you had the opportunity. High density food, freeze dried food. Obviously, these are reliable calories and they're just backup supplies. You don't know if the food you're producing in this space environment will provide these this specific amount of calories and nutrients that your body needs, all those carbohydrates, proteins, fibers, all that stuff. So this is why freeze dried food is really important to have. In addition to that, cultures like yeast and probiotics will help for our digestion and fermentation. You can't, you obviously can't produce fermentation just like that. So this will get us starting. And then electronics and microcontrollers, most of it is really composed of complex manufacturing. It'll just be easier to transport it from Earth, honestly. And then habitat framework, our installation, most of it is designed in our project. So, by using the Starship, we transport our habitats framework. And it's composed of specialized materials. So you can't have, say, I don't know, I talked about the aluminum, um, what was it? I forgot. Oh my goodness. It's the, yes, aluminum silicate dome. You'd have to transport that from Earth. And then finally, the battery packs, like the lithium ion packs, battery packs that I was talking about for energy storage. Now I'll talk about the management because our habitat can't function without crew members, obviously. So per our assignment, we have four. We have the chief engineer, the assistant engineer, the researcher, and the technician. The chief engineer obviously has the role to oversee our systems integration, to provide crisis response. They'll manage mission planning and timeline tracking. They'll perform diagnostics on power, waste, and air filter, um, and conduct emergency simulations and response protocols. Obviously, they're the ones who make the decision on what is going to go on in the center. Then we have the assistant engineer. The assistant engineer will assist and provide operational support to the chief engineer in whatever they need to do. But also it can have tasks like maintaining and checking on the solar panels, batteries, and electrical systems. If something is going on, then the technician will come in and fix that. Conduct daily maintenance routes, assist the safety checks, and manage water recycling. And then my researcher is actually the one who has the most jobs. So, but their role is specific to scientific experimentation, data collection, and life sciences. They'll manage the vertical garden, so track harvesting, track the plant's health, operate lab instruments like microscopes, sensors, data loggers, and if any of this is going haywire, then the technician comes in and checks that. And then also they'll conduct the testing of the soil and the regolith samples. Logging the data is also a really important aspect of it all. So, in order for people to understand if this is actually working or not. In addition to that, they'll conduct research on crew health and psychological wellness and log that data as well. And then the technician will handle all hardware repairs, rover readiness, and support systems that are needed in order to keep the station running. So, managing the garage module, repairing tools or 3D printed gear, inspecting the air filtration, temperature regulation, conducting the extravehicular activities. Say if something goes wrong on the outside, the technician will go and do that, obviously with the authorization of the chief engineer. Now, also, this is a team. A crew can't work if they don't work together. So some collaborative tasks are also really important, like daily crew briefings. We need to ensure that everyone knows what's going on in the station, providing weekly inventory assessments. So do we have a good amount of food? Do we have a good supply of energy? All that stuff. Shared cooking. Another thing that can benefit to that psychological impact that space travel can have on the human body. And then astronomy observations in the dome, it can't hurt them. Now, another really important task, and this is what they're gonna train for even before they leave Earth for the mission, is their astronaut training. So, in specific, the chief engineer, they all train in different topics, but they will all have a general understanding of everything that needs to get done. So, the chief engineer will be trained to understand habitat systems and diagnostics, but also to manage crisis leadership and planning. The assistant will probably have to train in water and power system support, as well as emergency fixes. The researcher must have a general understanding of plant biology, chemistry, soil and atmosphere analysis, help monitoring and data logging, and experiment design and reporting. And then the technician would need to train in rover system maintenance, tool repair and upkeep, filtration systems, EVA gear checks, all that stuff. But in the same way that they all have specific routines and general routines, uh, cross training is also really crucial. So the crew must train across roles, so engineering, medical operations, etc., in order to improve adaptability if something were to happen to one of these crew members. So that includes emergency response, first aid, and basic medicine skills, Martian EVA, cooking and rationing, and then obviously teamwork and conflict resolution. And here are just some YouTube videos that can be used to train astronauts. One of them is actually, I think it's titled Train Like a NASA Astronaut, and it teaches you every single little thing that NASA astronauts are taught and how they're chosen. Now I'll talk about the resources that are necessary for 1 week's time, and this mission is 5 days. So obviously water is a really important one. Drinking water, hygiene, cooking, all that stuff. So per person on average, it'll take 5 liters a day or a total of 100 liters for 5 days. The food and its dry mass per person is around 800 grams a day, and then a total of 16 kilograms or 16,000 grams per 5 days. Oxygen is another important one, and although this can be produced through recycled plant photosynthesis, this is just talking about a backup supply because NASA will always send a backup supply. So per person, you consume 550 liters a day of pure oxygen dioxide, so at 1 atmospheric pressure or ATM, with a total of 11,000 liters or 11 m meters cubed. And then also you have some additional necessities. So you have to take care of all the waste that you're producing. So managing that system, you from around 5 to 7 kilograms of solid waste, and then 60 to 80 liters of toilet water, which is why we very much need a recycling system. And then you want to have an emergency water reserve because again, NASA always likes to be cautious. So at least 20 liters of emergency water. Now, obviously, every mission has to have guidelines as to how it's going to function. Uh, and this goes with having all the protocols that these crew members have to follow. So this is something that we would agree with in the other stations. For safety and emergencies, we want to have to follow safety protocols. So ensure that everyone knows that, their suits have to be working, airlocks have to be used, monitoring of the systems. It's important, it's crucial that every single center is conducting daily system checks and that they're using their resources wisely. Most likely, we would be sharing all the energy that is being produced. So, using these resources mindfully because we don't want to run out. Also, everyone in the station must respect the closed loop systems. If contamination exists anywhere in the station, it's a risk everywhere. So we don't want that to happen either. Also, keeping close communication. Communication is probably one of the most important aspects of any type of relationship here on Earth or anywhere else. So that's important as well as sharing our research finding. If we're conducting different types of research, sharing that information would be good in order to, adjust for that energy consumption and stuff like that. Now, with those guidelines, we also need to have protocols. Uh, Specific protocols to my facility would be Doing those daily systems checks, so inspecting oxygen levels and guarding carbon dioxide absorption. I want to make sure that everything is working as it's supposed to be working. Also, monitoring the energy battery charge levels and power output, making sure that's working, make sure our backup supply is properly functioning as well. In terms of our vertical garden, rotating the crops for balanced nutrition and oxygen output, logging the plant health and the harvests in milligrams of biomass per day, as well as inspecting the hydroponic wastewater systems for any leaks or clogs. This goes into the general guidelines that is provided to the overall station, ensuring that contamination isn't happening. And then we have the garage and the energy bay operations. So conducting daily thermal regulation checks, making sure the temperature and the humidity sensors are working as they should be. And then also probably one of the most important ones is the airlock and the clean zone rules. So conducting those suit checks before entering the airlock, making sure you're not dying. Clean room gloves are required when working near the printer or the garden because these are very so the printer can be damaged very easily, and then the garden is our food supply, so you don't want to ruin that either. And then I have specific protocols or routines of the facility. Research station use, so you want to schedule blocks for equipment, who's using microscopes, analyzers, stuff like that, keeping that clear communication. Labeling and logging all experiments with the location, the date, and the purpose. You obviously want to know when you did the last thing. And if you're sharing these findings with the rest of the station, this is a really important thing to have. As well as securing the samples in sealed containers. You don't want to leak any of that contamination into the sterile environment. Some protocols of safety, because safety is always necessary. For my facility in particular, it would be, being careful of using the spiral staircase, so only one person on the stairs at a time during operations. And then mental and physical health monitoring. So morning group check-ins on energy, mood, and sleep. We want to make sure that everyone's giving their 100%. And then obviously, if we're having these astronauts working all day long, we can't expect them to be productive. So having some entertainment hours is also important. I'm allocating 1 hour of daily exercise mandatory for every crew member. Stargazing is also encouraged once per week for just, that morale boost. Trivia nights would be fun as well, board or card games. A journal time is one of the important things for tracking that psychological development, as well as reading. Reading can also help you pass the time. And then some of my protocols for food micro production. I loved what Anais had said yesterday on her protocols for food micro production. I think that's a really interesting research topic. But I'm just keeping it simple here. Daily plant care, so monitoring the pH, the moisture, and the nutrient levels of our plants. And recording, the plant growth status, any diseases or deficiencies, you want to cut those out before they spread. The water and nutrient management system, so logging input and output of water volumes, and just replacing the nutrient solution every couple of days. I think the standard's like 3 days. And then you want to control the environments that the plants are growing in. So monitoring the light spectrum, the intensity for optimal photosynthesis, all that stuff that you will learn through actually doing the research. Uh, I will have some guidelines for harvesting. So harvesting in small portions daily will ensure that there continues regrowth. And then also crop rotation and replanting. So following a 1 to 2 week schedule for seed germination and replanting, especially if you are propagating the seeds that you brought from Earth. And then the waste management system. You obviously want to compost unusable plant matter for filament or nutrient recovery, which will eventually come back to being used. And then some protocols for the 3D printing. As we are bringing these 3D printers from Earth, you want to ensure that you're not damaging them. So before you print, check the printer, clean the bed, load the filament, and use only approved files. Uh, you don't want to damage the system. When you're printing, you want to log the print time and the energy used. You also don't want to be printing all day long. After you print, you want to wear gloves to handle the prints and perform post-processing. So, sanding, sterilizing, stuff like that. Make sure the printer is clean afterwards. Um, this would be the job of the technician, but cleaning the printer weekly, calibrating it monthly to ensure that you're not wasting any filament. And then obviously safety aspects of it all is to never leave, especially with the high temperature prints, never leave the printer unattended. And then use ventilation and emergency stop if you so need it to, so that you're not causing a fire in your environment. Now, these are some spin-off technologies that I've designed to go accordingly with my facility. So a closed loop vertical garden. I've already talked a bunch about this, but this urban farming in food deserts or regions with limited arable land here on Earth would very much benefit from these vertical systems. It would yield to efficient food production with very minimal water and space usage. Another thing, compact water recycling systems. I think it's a big problem we have, and I've seen it here in the United States where drought-prone areas and sustainable housing would very much benefit from recycling all the gray water or urine even. It'll just drastically cut water waste. And then additionally, the modular and low energy habitats would, such as the affordable housing or disaster relief shelters, would benefit from this being climate resilient and rapidly deployable living units. Just a couple of months ago, we had a bunch of fires in the state of California, and that decimated a bunch of habitants' lives. So having these low energy habitats would have greatly benefited in that situation. Now, as well, training protocols for these crew members. When you are selected to be an astronaut, you do all this workforce development. You build versatile and self-reliant teams that can work together in the case of crisis. This is just as important in any other job here on Earth. In remote industries as well, it doesn't have to be anything STEM related, but just knowing how to deal with humans as a human is really, really um, crucial. Now, if we're following these guidelines in space, I think it'd be really wise to also apply them to our daily life here on Earth. So wasting nothing, reuse, recycle, and repurpose any materials before disposing them. I know, and I've seen this. I've lived in Honduras and in the United States. I'm from Honduras. Um, and specifically in the United States, I think it follows with the consumerist culture. People throw away stuff before, taking all that they can take from it. So conserving those resources, using minimal water, minimal energy, planning our meals efficiently, making sure that we're eating nutritious, low waste meals, still getting that caloric input. And being mentally and physically active is also really important. Um, it helps us with mental illness and physical health. And especially in confined settings such as in space, this is good, or people who work from home, who work remotely would benefit from being physically active. To always be prepared for emergencies. Emergencies can happen anywhere, so being prepared for them is the best thing you can do for yourself, and always stay curious and is another component, I think. Um, doing all this research in space, you also need to stay curious about the little things in your life. And then finally, I'm going to talk about the impact that this research experiment comes with. So, obviously, there's a couple of global goals that the United Nations put out a couple of years ago to ensure that we are achieving them all as a global community. And our Martian facility follows goals 2, 6, 7, 9, and 17. Follows a bunch of other mores, but I'm going to talk about those in specific today. For example, goal number 2, which is zero hunger. The vertical garden promotes sustainable agriculture and self-sufficiency. It would greatly benefit the Earth community. Goal number 6 is clean water and sanitation. So, that water recycling, that filtration, and those closed loop systems demonstrate the efficiency, use, and reuse of water. Goal number 7, which calls for affordable and clean energy. So, solar panel use and energy storage provides sustainable energy for the entire facility. I would say that in the past couple of years, I live in a small town, so you can't, it's not a big city, not everyone uses solar panels, but in the past couple of years, people have started to implement solar panels in their houses. And you can go for a walk, especially where I live, and see a bunch of houses that have solar panels and use that clean energy system. uh, Industry, innovation, and infrastructure, which is goal number 9. So the use of these advanced technologies like 3D printing and modular architecture fosters innovation and better infrastructure. And then finally, goal number 17, which is partnerships for the goals, collaborating on different types of modules and facilities mirrors the global cooperation for sustainability. It's funny, we all live in different countries, the US, the UK, France, India, Brazil, and we're all collaborating on this project together. It's the very same thing if we're in the Mars situation. We have different facilities and we're still collaborating for a common and general goal. And then I just have my personal and contact information. If you want to look at that, I have my LinkedIn, my email, and a couple of space pictures because how can you not have space pictures? So, but if you have any questions, I'd love to answer them.